Welcome to EDU World Space.
Here we are to approximate a wave function, a quantum mechanical wave function, as a so-called Fourier series. So that Fourier series is represented in just space, whereas usually there would just be three spatial parts and a time part. This is just a simplified one-dimensional particle with no time dependence. And our formula for adding up our sine and cosine functions is to take all odd sine functions and alternate them with a sine in between adjacent terms and keep doing this out to some odd n. So plus or minus sine of some big N times x. As mentioned, the quantity out in front is a so-called normalization factor that makes each wave function have a maximum close to 1, maybe exactly 1. And let's take a look at what this wave function looks like for different lengths of the series. So what I'll call figure A has n equals to 5, which means that the first three terms are added together. The second one has n equals 11, so we're basically going to double the number of terms that are added together for each subsequent picture. And I used a plotting program called Maple. It allows you to add summations and plot them with fair ease, very similar to something like Mathematica. Whoops, the third one is N21. So again, we're doubling the number of terms in between. And let's now look at the uncertainty principle. If this were, say, a particle in a box that was one-dimensional, and the length goes from 0 to about pi. If this was a particle in a box, let's think about the most probable location of the particle and the uncertainty. So we can see that the most probable location is pretty much in the middle of the box. And we can think about the width of that central peak as being like the uncertainty in the position. Okay, so it has a high probability of being found near the center. And what we can see as we double the number of terms is the uncertainty certainly goes down and roughly goes down by a factor of 2 between changes. So we'll say that the first uncertainty is approximately 1. It's a little bit over that. And the next uncertainty is approximately 1/2. And without measuring, we could say it looks to be about 1/4 in the third picture. And we don't know for sure, but it definitely looks like it's about 1/2 in the last picture. So these were all plotted pretty much on the same scale. So by eyeball comparison. Now, why is the uncertainty going down? The uncertainty relationship says that the product of delta x times delta p is of the order of h bar. Okay, so it's a little ambiguous, we'll say, but it's of the order of h bar. But the idea is if the uncertainty in position is decreasing, shouldn't the uncertainty in the momentum go up to keep the product fairly constant. And this is a known wave behavior. What you're practically doing is you're adding different wavelengths together. And the more wavelengths that you add together, the more uncertain your momentum is. And let's see how that works. So the de Broglie wavelength is given by P equals H over lambda. And in each of those terms, if you just take a look at the sine of x, for example, this is equal to the sine of 2 pi lambda times x. Can be the way it is written in terms of the wave number or the wavelength. So each term adds a wavelength. So, for example, sine of 3x adds sine of 2 pi times a new wavelength. Okay, and you could find each of those wavelengths, etc. So as you double the number of terms in the sum, you double the number of wavelengths in the system, in the function. And that increases the spread in momentum by roughly 2. So yes, and the visual way that you see that, of course, you could do a histogram of the momenta and wavelengths in the system and kind of get a spread from there. But the way it's evidenced is by the uncertainty in the position decreasing.